Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight, we begin a journey not just through time, but through deep time. The kind of time that doesn't tick by on clocks, but flows through rock layers, ancient oceans, and the silent folding of continents. We're going to follow the Earth, your Earth, from its very first moment, long before skies were blue or oceans had names, long before breath, long before bones, long before anything that could have looked up and wondered where it all began. But before we step into that story, that long, slow, breathtaking story, I'd love if you could take just a moment to like this video and subscribe if you enjoy these gentle explorations, and if you feel like it, leave a comment to let me know where you're listening from and what time it is for you right now. It's always a quiet joy to see where all our sleepy minds have gathered from. Now take a breath with me, in and out. Feel free to dim the lights, pull up the covers, or just let your eyelids grow a little heavier. There's no pressure to remember anything here. You can drift, you can dream. This journey is slow and wide and waiting. Let's begin. Not with a bang, but with a hush. Close your eyes, if they aren't already, and imagine this. There is nothing. Not poetic nothing, like a blank canvas or an empty stage, but the kind of nothing that doesn't even have the space to echo. No light, no sound, no time. And then, from that nothing, there is something. A flicker, a breathless spark, and suddenly a universe begins. Galaxies spin themselves into spirals, stars ignite, and in one quiet corner of it all, a young star stretches out its arms, gathering the dusty remains of past explosions. From that star, our sun, a disk forms, a swirl of gas and rock and ice, dancing around the brightness at the centre like moths circling a flame they don't yet know will warm them. This is where Earth begins. Not with green forests or blue skies, but with dust. Ancient cosmic dust. Drifting, colliding, clumping. There's no music here, just gravity. Patient and relentless. Pulling, pressing, shaping. You're not on the Earth yet. The Earth doesn't have a surface to stand on. It doesn't even have a shape, really. Not at first. It's just the possibility of a world forming in a slow spiral of light and heat. Sometimes we imagine creation as a sudden thing, a switch flipped, a curtain lifted, but real creation is quieter, it's messier, it takes time, and time in this story moves in different ways. 4.5 billion years ago, there was no one to mark a calendar, no one to say, this is the beginning, but still it began. Not with a sunrise, but with a coalescence, an assembling, particles binding to each other bit by bit until a planet was born. And not just any planet, a planet with the potential to do something no other has yet done, to cradle life, to nurture complexity, to one day grow minds that wonder about beginnings. That planet is ours. There will be fire, there will be ice, there will be silence so vast it humbles every sound you've ever heard. And eventually there will be breath. There will be forests. There will be footsteps. And you, yes, you, will be part of that story. But not yet. Tonight, we're going to travel through all of it. From the fiery origins of Earth to the first quiet stirrings of life. From magma oceans to microbial dreams. You don't need to understand everything. You don't need to follow every name or date. Just let the rhythm of the story carry you. Let the ancientness of it comfort you. Like a lullaby hummed by a planet far older than sleep. Time slips, it stretches, it folds itself into places we can't quite follow. But we're going to try, gently, slowly, together. So settle in, and let's begin the 4 billion year journey, starting from nothing and ending with the first flicker of something that looked a little like you. Before Earth had a name, or a shape, or even the soft blue of oceans, there was only dust. Not the dust you brush from a bookshelf, but ancient, cosmic dust. The kind that drifted in the dark long before stars had settled into constellations. These fine particles were the leftovers of forgotten stars, the ashes of long ago supernova, scattered across a vast nursery of creation. In a quiet corner of the young galaxy, that dust began to turn. Gravity, silent, invisible, and patient, started pulling things inward, slowly, gently. What began as scattered debris started to swirl around a newborn star, our sun, just beginning to shine. It wasn't the bright golden disk we see in the sky today. It was more like a pulsing furnace in the fog, cloaked in gas and fire, surrounded by a spinning disk of matter waiting for something to happen. This is what astronomers call a protoplanetary disk, a wide flat circle of dust and gas orbiting a star, full of the ingredients for planets, moons, and possibilities. But at this point, there was no Earth, no Mars, no Saturn with its delicate rings, only chaos and patience and time. The particles in the disk collided, bounced, stuck together, then broke apart and tried again and again. What sounds like destruction was actually how everything was made. Over tens of thousands of years, then hundreds of thousands, then millions, the dust began to gather into larger pieces. Pebbles, boulders, and eventually planetesimals. Baby planets, each one pulling in more and more mass as they orbited. There was nothing fast about this process. You could watch for a lifetime and see nothing change. But change was happening, quietly, deeply. One of those clumps, spinning slowly near what we now call the third orbit from the Sun, was beginning to outgrow the others. It had no oceans yet, no continents, not even a firm surface. But it had mass, and with mass came gravity, and with gravity came more mass, a spiral of becoming. This was Earth, not as you know it, but as a glowing embryo of stone and molten metal, taking shape in the dark. This process, the slow gathering of a planet, wasn't a series of explosive events. It wasn't the kind of birth marked by fireworks or drama. It was something gentler, more deliberate. Some scientists describe it as pebble accretion, a phrase that sounds like something geological but feels almost poetic. Earth didn't crash into existence. It softly clung itself together, layer by layer, through the persistent logic of gravity and time. Still, it wasn't peaceful. This was a rough neighbourhood in the early solar system. Other planetesimals were forming too. Some collided and merged, others shattered and scattered. The sky, if there had been one, would have been full of fire. But even in this chaos, Earth held on. It kept growing. Every collision added heat, and soon Earth's young surface was molten, a deep ocean of magma glowing with inner fire. And yet, even as it burned, it began to separate. Inside the growing planet, heavier materials like iron and nickel sank toward the centre. Lighter silicates floated upward. The Earth was beginning to organise itself, forming a core, a mantle, and a crust, though the crust was still thin, still unstable. These layers would someday allow for magnetic fields, tectonic movement, and the long, slow emergence of continents. But for now, they were only beginnings. Meanwhile, in the sky above, though there was no sky as we would see it, the protoplanetary disk was still rich with debris. Earth wasn't done changing. It had one more appointment with destiny. But that's for the next session. For now, imagine a world without air, without blue, without breath. Just a sphere of glowing rock spinning slowly in a vast dark nursery. No trees, no rivers, no names. But still, something precious was beginning. You, because everything you are, every cell in your body, every thought, every heartbeat, was made possible by this moment, by the quiet collapse of dust, by the silent pull of gravity, by the gentle persistence of matter becoming form. It's easy to forget how fragile planets are and how improbable it is that any of them hold life. But Earth, from the very beginning, was building something rare, something that could change, adapt, and eventually look back and wonder. Tonight, you're lying in a room, perhaps on a bed, with blankets, pillows, maybe a gentle fan humming in the background. You're surrounded by the comfort of the present. But beneath all that, beneath your feet, beneath the cities, forests, and oceans, is a story 4.5 billion years long. And it began here, with dust, with heat, with the quiet hope of a world waiting to cool. Sleep, like gravity, is gentle when you let it be. And like the birth of a planet, it doesn't need to rush. In the early darkness, Earth spun alone. Still young, still molten, still wrapped in the heavy breath of its own volcanic size, it drifted through space not as the blue marble we know today, but as a churning, red-hot world, restless and half-formed. There were no oceans yet, no winds, no trees to whisper or oceans to crash, just fire beneath and emptiness above. But Earth was not truly alone. Something else was circling the sun, something roughly the size of Mars, another growing world caught in the same cosmic nursery. It was called Theia, though it didn't have a name back then. Names came much later, when life had language and language had memory. Still, Theia existed, and it was on a path toward Earth. Slowly, quietly, over millions of years, it drifted closer. This was no accident. In the early solar system, orbits were chaotic, unkind, and often terminal. Worlds were still choosing who would stay and who would be scattered into rings of rubble. Some planets to be were flung outward, others were swallowed whole, but Earth was about to collide, not with destruction, but with transformation. Theia didn't skim past. It didn't graze or glance. It struck, a titanic, glancing blow, not a head-on crash, but a sidelong impact, like a dancer swinging their partner too far and too fast. The collision vaporized rock, shattered crust, and launched plumes of molten debris into space. Some of that material rained back down, fusing into Earth's body, but a great deal of it didn't. Instead, it formed a ring, a halo of broken Earth and scattered Theia, glowing and orbiting like a ghostly veil. And from that ring, something new was born, the Moon. Not all at once, and not as it is now. At first, it was a molten lump of silicate, coalescing from hot debris, slowly pulling itself into a sphere under the same quiet force that had once formed the Earth itself. Over time, it cooled, it settled, it stayed, and in doing so, it changed everything. We often think of the Moon as passive, a quiet companion, a nightlight. But in truth, the Moon is one of the most important characters in Earth's story. Its gravity pulled at our planet's crust and oceans, even when those oceans hadn't formed yet. It helped stabilize Earth's axial tilt, preventing wild swings in climate that could have made life impossible. It gave us tides, long before beaches or shells existed to notice them, and helped slow Earth's rapid spin, giving us longer days and more gentle seasons. It is hard to overstate how unlikely this is. Of the many planets in our solar system, Earth's moon is unusually large compared to its host. It shouldn't be here, not like this. And yet, here it is, rising and falling each night, keeping rhythm with our oceans, our calendars, our myths. And though it no longer glows with heat, it remembers. Every crater on the moon's face is a mark of time, impacts from a younger universe. Unlike Earth, which has weather and water and tectonics to erase its scars, the moon has no such erosion. Its face is a memory, a frozen witness to a past we can no longer see on Earth itself. Tonight, if the sky's clear, you might step outside and look up. You'll see the moon, quiet and pale, caught in its endless orbit. It seems still, it seems silent, but it's moving, always, slowly drifting away from Earth by about 1.5 inches every year, a slow farewell that will never truly finish. The moon, born of violence, has become a keeper of peace. It's strange to think that without that ancient collision, you might not be here. Life as we know it, with its cycles, rhythms and climates, might never have emerged. Our days would have been shorter, our axis more chaotic, our tides uncertain. All of this, all the stability we depend on, is tied to that one cosmic moment of impact. Sometimes things must break before they can balance. There is a kind of poetry in that. A planet and a phantom world collide, and from the wreckage, a companion rises, not in spite of destruction, but because of it. Not as a wound, but as a witness. So much of Earth's story is like this. Slow violence giving way to unexpected calm. Chaos becoming chemistry. Heat becoming habitability. And always, the quiet presence of time smoothing the edges. You don't have to memorize any of this. You don't have to remember Thea's name, or the angle of the impact, or the percentage of debris that stayed versus what drifted away. What matters is the rhythm, the slow unfolding, and the feeling that even in the most explosive moments, there's a kind of strange serenity waiting just behind. Just as Earth began to spin with a moon by its side, so too does your breath rise and fall now under the moon's same gaze. You are part of this rhythm. You are part of this story. You carry its gravity in your bones, its silence in your thoughts, and its heat, however faint, in your beating heart. The moon doesn't speak, but it has always been listening. The Earth, now with its new companion orbiting nearby, was still in its infancy. Though shaped, it was far from settled. Its surface wasn't solid in the way we know continents today. There were no rocks you could hold, no crust firm enough to walk upon. Instead, the young Earth was covered in a vast, restless ocean of molten rock, a magma sea that rolled and churned like a storm trapped in liquid fire. The world glowed not just from the sun above, but from its own inner heat, leaking out in waves that shimmered into the void. This heat came from many sources, from the relentless collisions during Earth's formation, from the gravitational energy of particles compacting into a sphere, from the decay of radioactive elements deep within. And so the Earth boiled, not like a pot on a stove, but like a planet that had yet to catch its breath. There was no sky as we know it, no blue, no clouds, no gentle sunrises. Instead, a thick atmosphere of vaporized rock, carbon dioxide, sulfur, and other volcanic gases hung above the churning magma. It wasn't clear, or breathable, or even visible from space in the way we imagine Earth today. It was dense, hot, and tinted with the colours of heavy metals and soot. If you could have looked down at Earth in this moment, you wouldn't have seen a planet as much as a glowing ember, shrouded in smoke, bleeding light into the void. And yet, within this chaos, structure was beginning to form. Inside the planet, gravity was quietly sorting things out. The heaviest elements, iron and nickel, sank downward, drawn inexorably to the centre. Lighter silicates and minerals floated upward, forming the earliest layers of what would one day become the mantle and crust. This process, known as planetary differentiation, is what gave Earth its internal organisation. A dense metallic core, a molten mantle swirling around it, and eventually a crust that could cool and harden into continents. This separation wasn't quick, nor was it quiet. As materials shifted inside the planet, they released even more heat. The core, compressing under its own weight, glowed with ferocity. The mantle convulsed with convection, and on the surface, massive volcanoes burst through the magma ocean, adding yet more gases to the toxic skies. It was as though the Earth was learning to breathe, and every exhalation came in the form of fire. These volcanic breaths were not just random outbursts, they were part of a planet becoming habitable. Each eruption released water vapour, carbon dioxide, ammonia, methane, all the raw ingredients for an atmosphere. And while this early atmosphere was anything but friendly, it was necessary. It trapped heat, yes, but it also began the slow process of balancing the Earth's surface. It shielded the planet from some of the harsh radiation of space, and it created a barrier, however thin, between Earth's fire and the universe's cold. Somewhere between these extremes, the blazing heat of Earth's core and the freezing silence of space, a kind of precarious harmony was forming. And then came the asteroids. Even after its primary formation, Earth remained under bombardment. Remnants from the solar system's chaotic formation still filled the skies, crashing into the young planet with force enough to remelt entire regions. Some of these impacts vaporized surface rock. Others may have delivered metals, elements, or perhaps even small amounts of water. Each strike was a punctuation in Earth's story, sudden, loud, and violent. But as time passed, the intervals between impacts grew longer. The space between chaos stretched wider. Earth, it seemed, was beginning to settle. The magma oceans thinned, cooling at the edges. Pockets of solid rock formed, not yet stable but thicker than before. And above, the dense skies began to shift. As water vapour continued to pour from volcanoes and accumulate in the air, the planet's upper layers started to cool, slowly, reluctantly, but inevitably. Eventually the atmosphere could no longer hold all the water it contained, and so it began to rain. But not in drizzles or gentle spring showers. Number. This was a rain that lasted for centuries, perhaps millennia, a rain born from steam and silence. It fell upon the hot surface in waves, each droplet hissing into vapour as it touched the molten ground, only to rise again and fall once more. Over time, the planet's temperature dropped just enough for some of that water to remain. Puddles formed, then lakes, then oceans. But that part, the soft arrival of water, belongs to the next chapter. For now, imagine the world at the edge of transformation. A place of fire, sighing through volcanoes. A place of storms, born not from clouds but from gas and ash. A place without trees, without bird song, without even blue sky, and yet still full of potential. There's something deeply comforting in this image, that even a planet as chaotic as early Earth could become a home, that even magma seas can cool, that even fire, given time, can give way to calm, and so can you. If you're still awake, your mind might feel full of molten images, of slow collisions, of distant thunder from an ancient world. But that's all right. Let the thoughts drift. Let them cool. Let them settle like crust across your own inner fire. Tomorrow the rain will fall. But for now, sleep beneath the heavy sky of Earth's first breaths, and know that even in your own quiet moments, something deep inside is slowly taking shape. Imagine a planet exhaling, not gently, like a sigh from lungs resting in sleep, but in long volcanic gasps, thick with steam, methane, carbon dioxide, and vapour rising from the churning crust. The Earth was no longer entirely molten, but it was far from calm. Its surface, still scarred with craters and glowing fissures, had cooled just enough for some rocks to harden into plates and slabs, precarious islands adrift in a sea of heat. Above this landscape the atmosphere swelled, not with blue skies or drifting clouds, but with a dense, opaque soup of gases. It was heavy, thick, and filled with vapour, not a drop of oxygen to be found. The sky would have looked nothing like it does today, more like the inside of a storm that never ended. Dim, red-orange, lit by volcanic fires below, and pierced occasionally by flashes from asteroid impacts still echoing through the solar system. But something was changing. The Earth's surface, though still restless, had cooled past a critical point. For the first time, temperatures fell below the threshold where water vapour could condense, and the atmosphere, that long-held breath of volcanic origin, began to return its gift. The skies opened, and it rained. It's difficult to picture how different this rain was from what you know. It wasn't soft, nor did it come with the gentle scent of wet leaves. This was primordial rain, born from steam and gravity. The drops were massive, falling into a world still hot enough to resist them. When they hit the ground, they didn't linger. They sizzled. They vanished in steam. Then they fell again, and again. Over time, centuries, perhaps tens of thousands of years, the planet cooled just enough to let those raindrops stay. What began as violent, hissing impact gave way to quiet puddling, then pooling, then spreading. Eventually, those puddles became lakes. The lakes found one another, merged and deepened, until, at last, the first oceans formed. Water, in many ways, is the true shaper of Earth. It cuts, it carries, it seeps and shifts. But before it did any of that, it simply gathered. Vast, silent, steaming bodies of water covered the planet's surface. They reflected no blue sky, because there was none. Only the swirling darkness above and the smouldering world below. And still, it rained. The water that filled these first oceans didn't come from just one source. Some of it perhaps arrived from space, carried by water-rich asteroids that collided with Earth during its early bombardment. But most of it, scientists now believe, came from deep inside the Earth itself. Trapped within the planet's interior during formation, it had been slowly released through volcanic activity. Every eruption, every crack in the crust, had whispered steam into the sky. These whispers became clouds. The clouds became storms. The storms became oceans. And with them something new was possible. Water is more than just liquid. It's a medium, a mirror, a shelter. In those ancient seas, dark, acidic, mineral-rich, chemistry had room to play. The ingredients of life, scattered and drifting, could now meet and mingle. Heat from underwater vents provided energy. Minerals offered structure. And the oceans cradled it all, softly, patiently, for millions of years. But the oceans weren't calm, not yet. They surged, heaved, crashed against hot shorelines. There were no beaches, no sand, only bare rock and steam, and the occasional flash of lightning from storms that wrapped around the globe. The early Earth was still wild, still dangerous, but now it had water, and that changed everything. With oceans came weather. With water came cycles, evaporation and rain, runoff and flow. For the first time, Earth was not just a place of fire, but a place of movement. A planet where things could gather, separate, mix, and try again. Life was not here yet, not quite, but the conditions were building. The stage was nearly set. If you could visit this early Earth, it would feel more alien than familiar. You wouldn't survive the air. You wouldn't recognize the sky. But if you could float above the steaming seas and close your eyes, you might still hear something recognizable. The sound of water meeting stone. A sound that has never left. A rhythm that still plays across every beach and riverbank, every tide pool and shoreline. That rhythm, the conversation between rock and rain, began here. We don't often think of water as ancient. It feels so every day, so ordinary. We drink it, wash with it, listen to it trickle or crash, freeze it into cubes or boil it for tea. But every drop in your cup tonight has known the world longer than we have. It has seen fire, storm, silence. It was steam in the sky before the sky had birds. It fell when the world was just beginning to cool. That same water, rearranged, recycled, and remembered, is inside you now, in your breath, in your bloodstream, in your thoughts perhaps, as they soften and stretch toward rest. The oceans have always been good at holding things: salt, secrets, dreams. And in the next part of Earth's story, they'll hold something more: life. But for tonight, let's stay here a little longer, in the hush after the rain, in the warmth of the planet beginning to rest. Outside your window, perhaps there's rain falling too, or maybe just silence. Either way, you're part of this planet shaped by the same water that once fell onto hot stone and refused to leave. Long before animals stirred in the forests, before anything walked, flew or dreamed, the first life on Earth began, not in sunlight, not in air, but in the dark. Imagine this: deep beneath the surface of the sea, where light could not reach, and the pressure of the water pressed down like the weight of time itself, the Earth exhaled. From cracks in the ocean floor, vents opened, not with fire, but with heat and mineral-rich water, warmer than the sea, laced with elements drawn up from the planet's still molten heart. These were not flames, but chimneys of warmth in a frozen void. And around them something extraordinary began to happen. Here in the dark, life stirred. It didn't begin as a creature. There were no eyes to blink open, no cells to divide just yet. Life's beginning was quieter, more like a thought forming for the very first time. It began with chemistry. Long, patient reactions between carbon and hydrogen, sulfur and iron, water and heat. Molecules that didn't just float past one another, but learned how to bind, to build, to repeat. Scientists call this the prebiotic world, a time when the ingredients of life swirl together like a simmering soup, rich with potential, but not yet alive. Among these ingredients, one molecule may have played a starring role: RNA. Unlike DNA, which serves as a more stable archive, RNA is versatile. It can store information like a script, but also fold into shapes that allow it to act, to cut, to join, to self-replicate. In a world with no enzymes, no metabolism, no cells, this ability to act and copy might have been enough to begin something new. Not life, in the way we usually mean it, but the possibility of life, whispered across warm water. Imagine a bubble. Not the kind that floats in the air, but a microscopic sphere made from fatty molecules. The kind that naturally clump together when they're surrounded by water. These bubbles, or protocells, could trap the ingredients of life inside them. They offered shelter, boundaries, a sense of place. And inside, the molecules could keep reacting, keep folding, keep trying. Some combinations lasted, others didn't. But over time, slow, invisible time, the ones that lasted became more common. This was not a single event. There was no one day when the Earth suddenly declared, "Now there is life." It was a process, long, winding, full of false starts and quiet successes. A molecule copying itself wasn't yet a cell, and a cell dividing wasn't yet an organism. But something had begun. A whisper had taken hold in the water, and Earth, for the first time, was no longer alone. These earliest forms of life didn't need oxygen. They didn't breathe as we do. Instead, they lived off the minerals around them, or harnessed the energy of chemical gradients near. Those deep-sea vents, they were simple. No nucleus, no organs, just strands of genetic code wrapped in membranes. But they were enough. They could grow, they could divide, they could evolve, and they did. Over time, these tiny pioneers spread beyond their warm, vented birthplaces. They drifted through the oceans, attaching to minerals, floating in the currents, multiplying in silence. They formed mats, colonies, invisible forests of microbes that covered the ocean floor and later the shallow coasts. They changed the chemistry of the world around them, absorbing, releasing, transforming. Even without consciousness, they were shaping their environment, and in doing so, they were shaping the future. From our perspective now, walking on continents, breathing air, watching the moon rise, it's easy to overlook what happened here. But the truth is, everything began in that quiet ocean. Every tree, every insect, every person, every breath we take is built on the success of these ancient replicators. They didn't need eyes to see, or brains to think, or lungs to breathe. They only needed time, and the sea gave them that. Even today, echoes of that beginning remain. Hydrothermal vents still exist, teeming with strange life that doesn't rely on sunlight. Deep-sea microbes continue to thrive in places humans can barely reach. And within our own cells, the machinery that reads our DNA, builds our proteins, and keeps us alive still carries the marks of its RNA-rich ancestry. Inside you, there are ancient systems that remember the ocean, even if you do not. It's humbling in a way, to know that life didn't begin with greatness. It began with persistence, with molecules trying, failing, trying again, with patterns that copied themselves just well enough to last, with chemistry that learned, somehow, to remember. If you listen closely, you might hear it, not with your ears, but in the rhythm of your breath, the pulse in your chest. That slow, steady rhythm began in water, in warmth, in silence. You're not separate from it. You're its continuation. Tonight, as your thoughts slow and your body softens, imagine those ancient seas. Imagine the darkness, not as emptiness, but as shelter. Imagine life, not as something that appeared fully formed, but as something that grew from warmth and patience. Let yourself drift with it gently, like a cell in a tide that has been moving for 4 billion years. The whisper that became life is still here. You carry it with you, even now. After life's first whisper stirred in the depths of ancient seas, it did not rise into a world filled with sunshine and blue skies. It rose into a world still cloaked in shadow, where the air was thick with carbon dioxide, methane, and sulfur compounds. Oxygen, the gas we so easily associate with life, was not only absent, but unwelcome. It would have been toxic to these early organisms, deadly in the same way that ammonia or chlorine would be to us now, and yet life didn't mind. In fact, it thrived. The earliest life on Earth existed in anoxic conditions, environments with no free oxygen at all. These were microbes, single-celled and profoundly resilient. They didn't breathe in the way animals do. Instead of using oxygen to process energy, they relied on other chemical pathways, fermenting nutrients, oxidizing sulfur, reducing iron. Their metabolisms were built for a world that we would consider utterly inhospitable, but for them it was home. They colonized the shallows and the depths, the warm vents and the cooling surfaces. They did not need light. They did not need air. They only needed time, water, and the chemistry of life. And with those simple ingredients, they painted the early Earth with their presence. Some of them we can still see. In parts of Western Australia and South Africa, there are ancient rock formations called stromatolites, layered mounds built by microbial communities that lived billions of years ago. These formations look like ripples frozen in stone, like the footprints of something that moved too slowly to disturb the water. They were made, layer by layer, by mats of microbes that trapped sediment and grew upward toward the light, even if they didn't need it to survive. With each generation, a new film of life would form over the last, building a kind of microbial monument, not because they intended to leave a mark, but simply because that was how they lived. Even today, stromatolites exist in a few remote corners of the world. In shallow, salty bays like Shark Bay in Australia, modern microbial mats continue this quiet, ancient ritual, rising, trapping sediment, growing again. They are living fossils, reminders that the first ecosystems were not made of trees and tigers, but of layers of film growing in the sunlight and surviving without oxygen. But surviving wasn't easy. The early Earth was a dangerous place. The sun was younger and more volatile, sending out intense ultraviolet radiation. There was no ozone layer to block these harmful rays, so the surface was constantly bathed in light that could damage or destroy fragile molecules. To live near the surface was to risk annihilation with every sunrise. Many early organisms found shelter beneath the sea, where water filtered out the radiation. Others lived deep within rock or clustered in sediments where light could not reach. And then there was the heat. With Earth still cooling and volcanic activity common, many environments were far hotter than anything we would consider comfortable. Yet these microbes adapted. They became thermophiles, lovers of heat. Some even became hyperthermophiles, able to survive in boiling water, in acidic springs, and in places where metals and gases would corrode most materials. They didn't just tolerate these conditions, they flourished in them. It's a strange thought, isn't it? That the earliest life wasn't fragile, but rather absurdly tough. We tend to think of life as something delicate, easily extinguished by extremes. But life, from its very beginning, was forged in extremes. It didn't seek comfort. It sought opportunity. Wherever chemistry could be persuaded to work, even slightly, even briefly, that was enough. And still, it multiplied. Across the planet, the microbial world expanded. Invisible, uncelebrated, but profoundly influential. These microbes altered the oceans, affected the atmosphere, and laid down the biochemical templates that would shape everything to come. They left traces in the rocks, chemical signatures, fossilized textures, isotopic clues, all of which tell us that life was not a rare pocket, but a planetary phenomenon. Given time, it spread everywhere it could. Not loudly, not quickly, but persistently. And it did all of this without oxygen. That's important to remember. Today we tend to associate oxygen with life, as if it's a universal requirement. But in truth, oxygen came later, and when it did, it was a catastrophe for many of these early organisms. To them, oxygen was a poison. Its rise would change everything, but not without cost. We will explore that soon. For now, rest in the idea that life does not require perfection. It requires possibility, a molecule that can replicate, a membrane to hold it, a little warmth, a little time, and resilience, not the kind that fights, but the kind that waits, adapts, and endures. You too are built from such resilience. Inside your body, in the mitochondria of your cells, in the enzymes that carry out your every breath, are echoes of these ancient microbes. You're not just a descendant of survival, you're a continuation of it. Tonight, as you lie in stillness, imagine a world without air, a sea without sky, a silence broken only by the bubbling of vents and the slow rise of microbial mats. Imagine creatures so small you could fit millions on the tip of a pin, each one carrying forward a message, passed down through molecules and membranes, all the way to you. They didn't need light. They didn't need oxygen. They just needed to begin. When you look up at the moon, with its pale face etched in shadow and light, you're gazing at a memory. Not just of light years or lunar myths, but of collisions. Ancient, countless collisions. The moon's surface has no wind, no water, no shifting plates to erase its history. Every crater is a mark left by a visitor from space, each one a sentence in a story written in stone. For decades, scientists believed that these craters told the tale of a violent chapter in the solar system's past. A time around 3.9 billion years ago, when a great storm of asteroids and comets rained down across the inner planets in what became known as the Late Heavy Bombardment, or LHB. According to this idea, Earth, the Moon, Mercury, Mars, all were battered in an intense burst of cosmic violence. It was thought to be a planetary reckoning, a sky full of falling rock and molten fury. But the Earth, with its oceans and atmosphere, does not preserve such memories the way the Moon does. Our planet is a forgetful one, constantly rewriting its surface through erosion, tectonics, and time. So we turn to the Moon, our quieter sibling, to help us remember. Lunar rocks brought back from the Apollo missions seemed to support the idea. Many of them dated to the same narrow window, as though a sudden spike in impacts had swept the solar system clean. The LHB theory took hold, colouring our picture of the early Earth as a dangerous, seething place, hostile to life, a planet barely able to catch its breath between cosmic blows. But then, slowly, new evidence began to soften that picture. More lunar samples, deeper analysis, and improved dating techniques began to raise questions. Was the clustering of impact dates an illusion, an artifact of where the samples were collected? Were these really signs of a single cataclysm, or simply the tail end of a longer decline in bombardment? Could it be that the Moon, and by extension, Earth, had been bombarded steadily, not suddenly? And if that were true, then something extraordinary followed. Life may have emerged not between strikes, not in a lucky pause, but during a relatively calm stretch in Earth's early years, a time of warmth, water, and quiet chemical unfolding. Not chaos. This shift in perspective changed how we imagined our own beginning. If the late heavy bombardment never truly happened, or happened more gradually, then the origin of life becomes not a miracle of endurance, but a natural extension of planetary stability. Not something that narrowly survived a rain of fire, but something that quietly developed while the skies cleared and cooled. There's still debate, of course. Some models still support a spike in impacts, perhaps triggered by shifts in the orbits of giant planets like Jupiter and Saturn. Others propose an early instability model, suggesting that the solar system rearranged itself even earlier, before Earth had finished cooling. In that version of the story, by the time oceans existed and chemistry had begun experimenting with life, the worst of the impacts were already over. Whichever way the evidence leans, one thing remains clear. Earth was not untouched, but neither was it entirely undone. Life, fragile, molecular, unseeing, emerged in a world that, while still restless, had moments of quiet. Long enough for complexity to begin, long enough for cells to copy themselves, long enough for warmth and water to host the possibility of a future. And if the Moon hadn't preserved its scars, we might never have asked these questions at all. There's something comforting in the thought that even in the grand chaos of the universe, there are places that remember. The Moon, though silent, is a witness. It shows us that while Earth may forget, some stories endure, not in words, but in craters, not in books, but in shadows on rock. And perhaps that's what science does best. It listens to the silence and asks it questions. It looks at stones and asks what they've seen. It peers into isotopes, crater counts, orbital dynamics, and quietly rewrites the stories we thought we knew. You don't have to pick a side in the bombardment debate. You don't need to remember dates or theories. Just hold this thought. The early Earth may not have been a battlefield, but a cradle. And life, in all its quiet strangeness, may have started not in the wreckage, but in the peace between storms. Tonight, as your own mind drifts between thoughts, between certainties, between dreams, consider this. Not every beginning needs a disaster. Not every miracle needs to be born in fire. Sometimes things start in silence, in soft waters, in slow, steady rhythms. Life, after all, is not always loud, and the sky, for all its memories of falling stone, is also the sky that holds the moon, gently, patiently, every night. The Earth does not keep time as we do. It doesn't count seconds or flip through calendars. It has no clocks that tick, no diaries in ink, and yet it remembers. It remembers in layers, in isotopes, in quiet crystalline structures buried deep beneath the places we stand. Time, for Earth, is not a number. It's a texture, pressed into stone, scattered in the dust of zircons, frozen in the delicate balance of atomic weights. If you want to know what happened long ago, long before life had bones or eyes or stories, you must ask the rocks, and they will answer. Not quickly, not loudly, but truthfully. Among the most remarkable of these timekeepers are tiny crystals called zircons. They are in some ways Earth's earliest memories. Some zircons found in Western Australia are over 4.3 billion years old, older than any mountain, older than any ocean, older than the moon's familiar face in our sky. These minerals, no wider than a grain of sand, formed in the crust when molten rock cooled. Inside their structure, they trapped traces of the world they came from, bits of uranium, which decay at a precise known rate. That decay acts as a clock, one that ticks not in seconds, but in half-lives, a slow, predictable fading from one element into another. By measuring how much uranium remains, and how much of it has transformed into lead, scientists can tell how old the zircon is. And sometimes, even more than that, they can tell what kind of environment it formed in. Was there water nearby? Was the crust cool enough to support oceans? What other elements were present in the molten rock? In this way, each zircon becomes not just a clock but a window. Through it, we see a world with no surface we can walk on, no skies we would survive, and yet a world that was already preparing for life. Other stones offer different kinds of memory. Some record the presence of carbon isotopes, subtle variations in the atomic makeup of carbon that can hint at biological activity. Life, even at its simplest, tends to favour lighter isotopes, like carbon-12 over carbon-13, and this preference leaves a mark. If ancient rocks show a strong signature of carbon-12, it may be because something living was once there, processing, growing, dividing. These traces are not fossils in the traditional sense. There are no bones to be found here, no shells or impressions, only tiny chemical whispers, a slight imbalance, a clue. Somewhere around 3.8 billion years ago in rocks from Greenland and elsewhere, these clues begin to appear, not universally, not without controversy, but often enough, and in patterns detailed enough, that many scientists believe life was already underway. Think of that. Before the moon had finished settling into its orbit, before the Earth's crust had fully stopped churning, life may have already found a way to leave its signature in stone. Not all records are chemical, some are textural. In Canada, in rocks over 3.7 billion years old, scientists have found what might be the faint outlines of microbial mats, tiny ripple-like patterns in sediment, shaped in ways that resemble the structures made by microbial colonies today. These aren't definitive fossils. They're suggestions, echoes. But when paired with isotope evidence, with zircon memories, with ancient chemical footprints, the picture begins to sharpen. It's not just that life existed, it's that it persisted, that it changed the world, molecule by molecule, long before it could write or speak or even see. You might wonder, how can such small things matter? But Earth's history isn't built on grand gestures alone. It's built on repetition, on tiny acts performed billions of times, a molecule replicating, a cell dividing, a microbe breathing in a way so subtle it changed the balance of an entire ocean. And the rocks remember it all. They remember the heat, the cooling, the rains. They remember the first oxygen, the first minerals pulled from water and deposited as stone. They remember the moments when things didn't quite work, and the long periods when everything stayed exactly the same. Because sometimes, stability is just as important as change. Geologists speak of deep time, not as a specific era, but as a way of thinking. To read the earth is to think like stone, to be patient, to accept that meaning doesn't always arrive in a single layer, but across a sequence of them. Each stratum builds on the one below. Each one holds its place in a rhythm so slow it slips beneath our usual awareness. And yet here we are, in a world built from that rhythm. Breathe in and know that the oxygen you take in exists because of 1 billion years of microbial work. Breathe out and know that the carbon you release has moved through plants, animals, volcanoes and stones far older than memory. You're not separate from this story. You are part of its ongoing chapter. Tonight, As your thoughts slow, as the room quiets around you, imagine the rocks beneath your city, your forest, your bed. Not as cold or lifeless, but as filled with memory. Imagine holding a zircon in your hand, no larger than a grain of sand, and knowing that it has seen things no eye ever has. Earth may not speak with words, but it tells stories in minerals, in crystals, in isotope ratios and fossil shapes. And when we listen, truly listen, we are hearing the deepest history of all. There are moments in Earth's history that do not announce themselves with fire or thunder. No great collisions, no frozen oceans, no roaring volcanoes, just quiet work, repetition. Something small doing something simple, again and again, until the world changes. Such was the arrival of cyanobacteria. They were not remarkable to look at, microscopic, thread-like, drifting in the sunlit shallows of ancient seas. But inside their tiny green-blue bodies, something revolutionary had taken shape, the ability to use sunlight to split water, capture carbon dioxide, and release oxygen. It was called photosynthesis, and in those days it was dangerous. Oxygen, as strange as it may seem, was not always the giver of life. For the early Earth, thick with methane, ammonia, and carbon dioxide, it was an intruder, a reactive, corrosive gas that could interfere with the fragile balance of chemical reactions that supported life at the time. To the anaerobic organisms that had thrived in oxygen's absence, it was toxic, but to the cyanobacteria, it was simply a byproduct. They breathed sunlight, built sugars from carbon, and released oxygen like a quiet sigh. And they kept going. Every day, every tide. At first, the oxygen didn't go far. The ancient oceans were filled with dissolved iron, and when oxygen met it, they reacted. The iron rusted, not into flakes or beams, but into vast underwater layers of red iron oxide slowly settling into bands. These layers, known today as banded iron formations BIFs, are found in rocks billions of years old. Striped and solid, they are Earth's first breath written in stone. Long before the air turned blue, the oceans turned red. This process took time. A long, long time. For hundreds of millions of years, the oxygen produced by cyanobacteria never reached the sky. It stayed trapped in the sea, binding to minerals, dissolving, reacting. It was like filling a room with perfume. But the room was vast and everything inside it absorbed the scent. Only when the absorbers were saturated, when the iron had rusted and the sinks were full, could the oxygen begin to accumulate in the air. And when it did, the Earth began to change. This turning point, around 2.4 billion years ago, is called the Great Oxidation Event. It wasn't sudden. It didn't happen in a year or even 1,000 years. It was slow, persistent, and quiet. Oxygen levels didn't leap. They crept. A breath that took millions of years to draw in. But for the first time, the atmosphere held free oxygen, and with it the seeds of future lungs, future fires, future skies. It's hard to imagine a change so profound, so essential to life as we know it, happening without drama. But that's the nature of slow revolutions. No trumpet sounded when the air became breathable. No flag marked the beginning of animal life. Just tiny cells in warm water, catching sunlight and exhaling something new. Their influence spread. Oxygen seeped into the oceans, into the shallows, into the sky. It reacted with methane, thinning the planet's greenhouse blanket. It oxidized minerals, shaped chemistry, set the stage for more energy-rich metabolisms. But it also brought endings. Many anaerobic organisms, adapted to a world without oxygen, could not survive this shift. Some retreated into anoxic pockets of sediment and salt. Others went extinct. The first global extinction, in a sense, caused not by impact or ice, but by photosynthesis. And still, the cyanobacteria kept breathing. They formed mats, layered structures known as stromatolites, which had already existed for over 1 billion years but now expanded into new environments. They paved the way, quite literally, for new forms of life to emerge, in an atmosphere gradually growing more complex. We owe them everything: the air we breathe, the energy our cells release, the ozone that shields us from radiation, the rust in our soil, the iron in our blood, all traceable to these ancient architects of the biosphere who asked for nothing, made no noise, and left behind a planet transformed. Tonight, if you walk beneath a sky brushed with stars or sit by a window listening to the wind, remember that this air is not inevitable. It was made, not all at once, but molecule by molecule, breath by breath, over millions of years. Not in a lab or a forge, but by blue-green algae floating in silent water. Their breath became your breath. Their legacy, invisible but everywhere, surrounds you even now, in the rusted earth, the singing lungs of trees, and the slow, steady rhythm of your chest rising and falling. The world didn't change because someone commanded it. It changed because something small kept going. Quietly, gently, persistently. And in that rhythm, life learned to breathe. It might seem strange that a planet warmed by the sun, wrapped in volcanic breath and stirred by currents of life, could fall silent under ice. But it did. Not just once, but more than once. Earth entered a deep stillness. And the first time it happened, it was because the world had learned to breathe. It began slowly. As cyanobacteria filled the oceans with oxygen, something unexpected occurred. Oxygen, in the presence of methane, one of the atmosphere's most potent greenhouse gases, doesn't just linger politely. It reacts. It breaks things apart. Over time, as oxygen increased and methane declined, Earth's warming blanket thinned. The sunlight still came, but the heat no longer stayed. Temperatures fell. Glaciers crept outward. Polar ice reached toward the equator, and eventually nearly all of Earth's oceans froze over. This was not a winter, nor even an ice age in the modern sense. This was something far deeper, more complete. A snowball Earth, blanketed in white, reflecting the sun's warmth back into space. This first great freeze is known as the Huronian glaciation, and it began around 2.4 billion years ago, lasting, in pulses and cycles, for nearly 300 million years. The air was thin, the light was dim, the seas were silent, and life, once again, faced a test it did not see coming. But life had already learned how to wait. In the quiet beneath the ice, microbes continued. Some clung to volcanic vents on the sea floor, where heat still rose from the planet's core. Others found refuge in cryoconite holes, small pockets of liquid water on glacier surfaces, warmed by the sun and insulated by a crust of dust and dark microbial film. Still others may have survived in subglacial lakes, sealed beneath kilometres of ice, where warmth from below kept water in motion. These refugees were not comfortable, but they were enough. Life shrank to fit the spaces it was allowed. It adapted slowly, silently. It learned to make do with low light, little warmth, and limited nutrients. It did not demand abundance, it only required possibility. And eventually, Earth exhaled again. Volcanoes, ever patient, continued their work beneath the ice. They released carbon dioxide, which accumulated in the atmosphere, unchecked by the weathering processes that normally draw CO2 down. With time, the planet warmed. The ice began to melt, and once again, water flowed freely across stone. But something had changed. The memory of the freeze remained, not just in rocks and isotopes, but in the resilience of life. The creatures that had endured now carried with them the adaptations to survive low temperatures, to function in low oxygen environments, to persist even when the world turned against them. The Earth too had changed. The glaciers had scraped the surface raw, exposing fresh rock to the elements. Rivers carved new paths. Oceans circulated differently. The planet's chemistry had been reset, not unlike a pause in a song that allows a new melody to rise. And oxygen, though it had caused the freeze, had not vanished. It returned slowly, cautiously. A little more with each breath of the biosphere. A little more with each surviving colony of photosynthetic cells. Its second rise would be quieter, more balanced. But its presence now was undeniable. The world had learned something. That breath is not without cost. That life brings with it change, and change brings consequences. And yet, those consequences are not always final. Sometimes, they are simply transitions. If you were to stand on Earth during this ancient deep freeze, if you had eyes that could see through time, you would see a world almost unrecognizable. White where it was once red, still where it was once boiling. Yet beneath the stillness, motion remained. Beneath the silence, whispers of metabolism, of replication, of persistence. And that perhaps is the greater miracle, not that life began, but that it endured. Tonight, as you lie still, as your room cools with the coming dark, you may find yourself wrapped in quiet. And in that quiet you might imagine Earth, vast and white, drifting through space like a frozen seed, carrying within it the memory of warmth and the potential for spring. You are, in some way, the continuation of that potential, the ability to endure a long winter, to change the air and then learn to live in what you've made, to adapt not just to place, but to time. These are not lessons we invented. They are part of us, inherited from microbes that huddled in cracks beneath the sea and waited. They teach us this, that warmth returns, that silence ends, that the longest nights are not empty, only slow. And when the thaw came, Earth did not go back to what it was. It went forward. After the ice receded and the world took another breath, something extraordinary began to unfold, not in thunder or spectacle, but within the quiet interiors of cells. Life, until now, had been remarkably simple. Single cells floating, drifting, absorbing, dividing. Tiny spheres of chemistry wrapped in membranes, each doing its work with admirable patience. But even the simplest life holds within it a certain restlessness, a hunger not just to survive but to expand, to try something new. And around 1.9 billion years ago, life did just that. It became complex. The first eukaryotic cells emerged, cells with internal compartments, with a nucleus to house DNA, with tiny energy factories called mitochondria humming quietly in their cytoplasm. Compared to the streamlined prokaryotes before them, these new cells were palaces, not castles of power, but homes of cooperation. Their story begins, strangely, with an invasion. At some point, perhaps many times, in many places, one kind of microbe slipped inside another, not as a predator and not as prey. At first, it may have been a mistake, a temporary arrangement. But instead of destroying one another, the two cells learned to live together. One provided protection, the other provided energy. This is the heart of the endosymbiosis theory. The idea that mitochondria and later chloroplasts in plant cells were once free-living bacteria. And now, billions of years later, they still retain traces of their independence. Mitochondria have their own DNA. They replicate separately. They carry echoes of the life they once lived alone. But together, these partnerships made possible something entirely new. Eukaryotic cells were larger, more complex, and far more versatile. They could store more genetic information. They could specialize. They could interact in new ways, not just with the environment, but with each other. And so, slowly, the possibility of multicellularity began to emerge. At first, these cells simply clumped together, like algae forming threads or blobs. Then some began to divide labour. A few cells specialised in anchoring, others in feeding, others in reproducing. Over long stretches of time, these loose gatherings became coordinated communities, the first tissues, the earlier steps toward plants, animals, and everything in between. We find their traces now in ancient rocks, not bones or shells, but fossils of impressions, of organized shapes, sometimes spherical, sometimes spiral. Names like Grapania, Terpania, and Bangiomorpha may not be familiar, but they are among the first visible signs of complexity. Grapania spiralis, dated to nearly 1.6 billion years ago, may have been a kind of algae, a ribbon of cells coiling gently in the water, simple by our standards, but unimaginably advanced in its own time. Bangiomorpha, appearing around 1.05 billion years ago, shows signs of sexual reproduction, not just copying itself, but combining with others, blending genes in ways that made evolution faster, more diverse. These were not organisms in a hurry. They lived in a world still dominated by microbes, by slow chemistry and long winters. Oxygen was rising, but still rare in many places. Nutrients were uneven, but inside those eukaryotic cells, something rich was brewing. Membranes within membranes, DNA coiled in quiet, mitochondria whispering energy, chloroplasts humming with captured light. It's humbling to consider how much of you is built on this architecture. Your nerves, your muscles, your thoughts, all powered by mitochondria, all housed in eukaryotic walls, all evolved from a quiet agreement struck 1 billion years ago. The very idea of being made of many parts, of collaboration, is older than multicellular life itself. And it wasn't just a structural change. Complexity allowed for communication, for memory, for shapes that could respond to the world around them and even begin to influence it. This was the beginning of a long conversation between life and its environment, a dialogue that would one day give rise to sponges, to corals, to fish, to mammals, but only because it began with cells learning to live together, with life folding inward, building compartments, nesting functions like rooms in a house. If you close your eyes tonight and imagine the inside of a cell, it may not look like much. A bit of gel, a few specks, a round centre. But know that it is a world, a soft, bustling world of purpose and motion. You're made of trillions of them, each with their own mitochondria, each tracing their lineage back to a moment of mutual trust. Not conquest, not force, but coexistence. The rise of complex cells wasn't a shout, it was a joining of hands, and in that gesture the future unfolded. Time equals 2.0 seconds. If you were to compress the entire history of life on Earth into a single book, the chapter between 1.8 and 0.8 billion years ago might seem, at first glance, uneventful. This stretch of time, lasting 1 billion years, has been given a name that sounds almost dismissive, the boring billion. But time, like stories, is often misunderstood when it moves slowly. This was not a chapter of silence. It was a chapter of subtlety. During this billion-year period, the world did not witness dramatic bursts of new body plans, no vast extinctions, no continents flipping upside down in fiery revolutions. But it was a time of deep preparation, like the stillness of breath before the next great leap. The Earth, now partially oxygenated, had oceans layered like a cake. The top layers, bathed in sunlight, held small amounts of oxygen, just enough to support photosynthetic life and some simple eukaryotes. But beneath, in the vastness of the deep, oxygen vanished. There, anoxic waters remained, often rich in hydrogen sulfide, the same gas that gives rotten eggs their smell and lethal to most forms of complex life. This stratification made the oceans a world of contrasts, light and shadow, air and poison. And in these conditions, microbes continue to thrive. Sulfur-loving bacteria in the depths, algae and plankton near the surface, forming the quiet infrastructure of planetary metabolism. They cycled nutrients, balanced gases and shaped the chemistry of seas and skies. To call this boring is to forget how slow, quiet work lays the foundation for everything else. It was during this time that life refined itself. Multicellular organisms didn't just appear, they persisted. Some formed filaments, others began developing signaling mechanisms, ways for cells to communicate and organize. Sexual reproduction, which had appeared earlier, became more common, increasing genetic diversity and allowing evolution to probe new possibilities. Inside cells, gene regulation systems evolved, tools that let organisms turn on and off certain traits in response to their environment. Think of it as the earliest form of flexibility, of adaptability written into code. These systems didn't make headlines in stone. They left no obvious fossils. But they made future complexity possible. The continents too were moving. Supercontinents came together and slowly pulled apart again. Rodinia, one of the earliest massive land masses, formed toward the end of this period. Its creation would later influence ocean currents, climates, and the next dramatic chapter in Earth's story. But for now, its slow assembly shaped winds, rainfall and erosion patterns in subtle, persistent ways. Above all, the world was learning to stabilize. Oxygen levels, though still low by today's standards, hovered and occasionally spiked. The biological and geological systems regulating it were locked in a kind of negotiation. Photosynthesizers created oxygen, volcanic activity, and deep ocean bacteria consumed it. And somewhere in between the balance held. Even the very structure of ecosystems began to change. Symbiosis became more common, not just in individual cells, but in entire communities. Lichens may have begun forming, humble partnerships between fungi and algae, quietly breaking down rock into soil. Life was beginning to shape the land, not just react to it. These weren't fireworks, they were roots. When people think of revolutions, they often imagine the noisy kind, sudden, dramatic, full of upheaval. But sometimes the most profound transformations come slowly, like water carving a canyon, like dust becoming topsoil, like life learning, over 1 billion years, how to be ready for what would come next. You can think of this boring 1 billion years like the long silence before dawn, the air cool, the stars still bright, the first birds not yet stirring. But within that stillness there is motion, there is growth, there is breath, held just long enough to make the next exhale meaningful. Tonight, as you lie still, not rushing, not seeking, you're participating in the same rhythm. The quiet between events is not nothing. It is the space where things prepare, where foundations deepen, where balance is found. In the end, the boring billion is only boring if you measure life by noise. But if you listen more closely to the molecular music, the whispered innovations, the subtle stirrings in shallow water and dim-lit stone, you'll find a planet rehearsing for brilliance, and you'll find life, as always, waiting with patient wonder. After 1 billion years of quiet breathing, of oxygen slowly threading itself into oceans and life inching toward complexity, the Earth shivered again. Not from the inside. This time the cold came from the sky. It began with Rodinia, the ancient supercontinent. Over millions of years it started to fragment. Pieces pulled away from one another like drifting puzzle parts on a global scale. And as they did, something subtle but significant happened. Fresh rock was exposed to the air and rain. Rain, falling over bare stone, doesn't just soak the ground. It reacts. It draws carbon dioxide out of the atmosphere, dissolving it into rivers, carrying it to the oceans, locking it into sediments. It's a slow, quiet process, but one that matters deeply. The more Rodinia broke apart, the more carbon dioxide was pulled from the sky. And as CO2 declined, so did the planet's ability to stay warm. The sun, still fainter in those days than it is now, could no longer keep the world from cooling. Ice began to spread, At first it clung to high latitudes, to mountain tops and polar shores, but then it crept closer to the equator, across continents, into oceans. The white grew brighter, and with it the world reflected more and more sunlight back into space, a feedback loop of cold feeding cold, until eventually almost the entire planet froze. This was the Cryogenian period, named after the Greek word krios, frost. It began roughly 720 million years ago, and may have lasted for as long as 85 million years. During this time, the Earth was locked in ice from pole to pole. Glaciers reached the tropics. The oceans themselves were covered in kilometres of frozen crust. Only the deepest waters remained liquid, warmed faintly by the Earth's internal heat. To stand on such a planet, if anyone could, would have been to see a world transformed. No green, no blue, just white. Endless, brilliant, silent white. But beneath that silence, life endured. Volcanoes, as always, did not stop. They continued to release gases into the atmosphere, including carbon dioxide. But with the oceans sealed beneath ice, and with weathering halted by the global freeze, nothing pulled that carbon back down. Slowly, over millions of years, CO2 built up. The greenhouse effect returned. The ice began, ever so slowly, to melt. And as it did, the world breathed again. The transition would not have been gentle. Some models suggest the Earth may have warmed quickly, perhaps even too quickly, with rapid melting, intense rainfall and dramatic shifts in ocean chemistry. Glacial runoff carried dust and nutrients into the sea. Dormant life stirred. The quiet under the ice gave way to bloom and change. But here, in this moment, before the thaw, let us stay for a little while longer. Imagine the frozen Earth not as dead, but as resting. Beneath the ice, thermal vents still glowed, small and steady. Around them, life held on, bacteria, archaea, simple eukaryotes, not flourishing, perhaps, but surviving. The same endurance that had carried life through fire and bombardment now carried it through cold and darkness. In places where the ice was thin or fractured, sunlight might have pierced through, faintly, dimly, like moonlight through frosted glass, enough to warm pockets of water, enough to keep a rhythm alive. Some scientists believe cryoconite holes formed even in this frozen world, small melt pools on the glacier's surface, warmed by trapped dust and dark microbial mats. It's possible, too, that beneath the ice sheets subglacial lakes formed, pressurized by the weight above, warmed by geothermal energy below. These lakes could have become isolated sanctuaries, entire ecosystems hidden beneath kilometers of silence. We cannot say for certain what those life forms looked like. We have no fossils from within the ice. But we know that life persisted, because when the Earth emerged from its icy slumber, life was waiting, ready not just to continue, but to bloom. In many ways, the Cryogenian is less a story of ice and more a story of pause, a long inhale before the exhale of diversity, a rehearsal for resilience, a reminder that stillness is not the absence of movement, but the storing of strength. Tonight, as your body lies still, perhaps you can feel some kinship with the Earth of this time, quiet, waiting, gathering warmth within. The cold outside is not the end, only the beginning of transformation, and when the ice melts, whether in the mind or in the world, something new will rise. Earth has frozen before and thawed. It has grown quiet and then sung again. So too, perhaps, can we. When the great glaciers began to crack, it did not sound like thunder. It sounded like the slow, steady sigh of a planet waking up. For tens of millions of years, Earth had been a world of silence and ice, a pale marble adrift in the dark, wrapped in layers of white, with only the faintest signs of motion hidden beneath. But even in that cold, even during the deepest quiet, life had not stopped. It had simply waited, in the warmth of ocean vents, in dark lakes beneath glaciers, in pools of light that melted their way into the snow. And now, with the return of warmth, life began to move again. The Cryogenian period, which had stretched from around 720 to 635 million years ago, had left its mark. The glaciers, when they finally began to melt, did not vanish all at once. They retreated slowly and then more quickly, carving valleys and flooding basins. Their meltwater rushed into the oceans, carrying with it a bounty of nutrients, iron, phosphorus, and other minerals that had been locked away under the ice. This sudden infusion of material into the seas was like opening a window in a still room. Sunlight reached into waters that hadn't felt it in millennia. Nutrients mixed into surface layers, and microscopic life responded. Algae, simple photosynthetic eukaryotes, bloomed in radiant green waves. These early plants were not trees or flowers or ferns. They were soft-bodied and tiny, drifting with the currents, but they brought with them the ability to turn sunlight into sugar, to build themselves from air and light. They multiplied in spirals and films, forming the foundation of a new oceanic food web. This was a renaissance beneath the ice, a rebirth not of art, but of energy. It wasn't just beauty. These algae exhaled oxygen, shifting the atmosphere again, accelerating the planet's slow transformation into a world that could one day host lungs as limbs and language. The oceans, once stratified and still, began to circulate. Melting ice mixed surface waters with the deep. Cold and warm currents swirled together, bringing nutrients up from the bottom and oxygen down from above. For the first time in hundreds of millions of years, the seas became truly alive, dynamic, breathing, evolving. It is difficult to overstate how important this was. So much of complex life depends on nutrient cycling, on oxygen, on circulation. Without these flows, energy stagnates, diversity falters, but with the sea stirred back into motion, Earth became a canvas again, ready for new forms, new structures, new experiments. The stage was set, and quietly, in the shallows, multicellular organisms began to take root. Some were algae forming long chains or sheets. Others were perhaps early fungi weaving their filaments through water and sediment. These were not animals yet, but they were building toward complexity, step by soft step. We can imagine these first communities like ancient forests beneath the sea, not with trunks and leaves, but with delicate fronds and threads, swaying in rhythm with tides. A forest of green and gold drifting just beneath the surface, invisible from above, but reshaping the world below. And while most of these organisms left no fossil trace, we know they existed because of the chemistry they changed, the oxygen they added, the isotopes they nudged ever so slightly in the sedimentary record. The rocks remember, even when the bodies have vanished. Some of the earliest signs come from the Trezona Formation in Australia, layers of rock that capture the end of the Cryogenian and the beginning of the Ediacaran period. These layers show sudden shifts in carbon and sulfur isotopes, which hint at massive biological activity. It's as if life, long held back, suddenly leaned forward, not with a shout, but with a breathless gasp. Earth, once again, had become a world of potential, and yet this wasn't a return to what had been. It was an emergence into something new. The freeze had not merely paused evolution, it had pruned, reshaped, selected. Only the hardiest forms survived the ice, and when the warmth came, those forms flourished. The result was not just a resumption, but a transformation. You can think of it like a long winter's garden. Buried under snow, the roots sleep. But they don't forget. And when the sun returns, what blooms is not identical to what came before. It is richer, more vibrant, more aware of what it means to endure. Tonight, as your breath settles and the night deepens around you, imagine this earth, thawing, stirring, glowing with the soft green light of algae in bloom. A renaissance not in cathedrals or canvas, but in cells, in currents, in quiet resilience, no fanfare, no applause, just the sea, breathing again. When life returned in full after Earth's long sleep, it did not rush into familiar forms. It didn't sprout claws or eyes or bones. It emerged as something far stranger, delicate, soft, and utterly unlike anything we see today. This was the Ediacaran period, beginning around 635 million years ago, and lasting until the dawn of the Cambrian explosion at 541 million years ago. In this window of deep time, Earth was once again a world of water and light, but now with more oxygen, more nutrients, and a blank biological canvas. And into that space, life began to dream. But what it dreamed was strange. We call them Ediacaran organisms, and to describe them is to step into the pages of a surreal storybook. They were neither plants nor animals as we know them. They had no eyes, no mouths, no skeletons. Some had no clear top or bottom. They lived on the seafloor, in the shallows, in the dark, flat world between sediment and water, and their bodies were soft, delicate, and patterned in fractals. One of the most iconic among them is Dickinsonia. Oval-shaped, segmented like a pill bug made of silk, it grew up to 4 feet long and lay pressed flat against the ocean floor. It had no obvious limbs or organs. For a long time, scientists weren't even sure whether it was animal, plant, fungus, or something entirely different. Only recently did biochemical traces, including cholesterol molecules, confirm that Dickinsonia was indeed an animal. But if so, it was unlike any animal alive today. Then there were the rangermorphs, branching, fern-like creatures that looked more like abstract sculptures than living beings. Some resembled feathers, others fractal trees. They grew in fans, in fractal spirals, each branch splitting again and again into smaller echoes of itself. Yet they were soft-bodied, immobile, and absorbed nutrients directly from the water, like living fractal sponges filtering without mouths. And there was Kimberella, a small slug-like creature with a more familiar shape. Unlike Dickinsonia, Kimberella had a clear top and bottom, a front and back. It likely crawled, grazed, and left behind feeding trails, hinting at the first stirrings of directed movement, of purposeful behaviour, of muscle against mud. All of these organisms lived in a world we would not recognise. The seas were different, the chemistry was different. Even gravity may have played differently across such delicate, squishy creatures. Most of them lived on microbial mats, carpets of bacteria that coated the seafloor like thin living skin. The Ediacaran Sea was not a place of predators and prey. There were no teeth, no skeletons, no chases, just drifting currents and slowly pulsing forms, existing in a quiet equilibrium. They didn't leave bones behind. Their fossils are found as impressions in ancient sandstone, like hand-pressed fabric on wet clay, a ripple, a fold, a ghost of something that once lay still. And yet, from these gentle outlines, we have learned so much. We've learned that life experimented long before it standardized, that symmetry, segmentation, and complexity appeared before nervous systems, long before eyes or shells, that there were whole worlds of form and function that didn't survive, not because they were failures, but because they were early drafts. You might think of this time as earth sketching, not a final painting, not the finished novel, but loose, intuitive lines across a page. Life trying out ideas, not hurried, not afraid, not aiming for efficiency. Just exploring what it could be. Some of these experiments didn't lead anywhere. The rangermorphs, for example, have no known descendants. Their lineage ended when the seas changed again. But others, like Kimberella, or organisms with bilateral hints, may have been early steps toward animals with legs, nerves, and coordinated movement. There's something poetic in this, that the path to lions and whales and birds might have passed through faceless ovals and living fractals, that the first creatures to try being animal didn't do it with eyes or jaws, but with patience, with soft bodies and strange symmetry, and a willingness to lie still and let the water speak. Tonight, as you close your eyes, imagine those ancient seas, still, diamond-sized shallow, with ripples of light sliding over the seafloor, over mats of bacteria, over soft-bodied shapes that swayed and pulsed, absorbing the world through every inch of their skin. There were no sounds, no screams, no flapping fins, only shapes, slow motion, the quietest kind of life. And even if those creatures are gone now, their story remains, not just in fossils, but in you, because life does not forget its experiments. Somewhere in your DNA, in the shape of your body, in the way your cells respond to light and pattern, there are echoes of those early forms. Life does not build only from winners, it builds from memory. And the Ediacaran, for all its strangeness, is a memory worth keeping. In the quietest corners of the Ediacaran Sea, beneath soft-bodied mats and strange alien creatures without faces, something small stirred. It did not shimmer, it did not rise, it did not glow or tower, it simply moved, not as drifting plankton, not as falling sediment, but with intention. Left, right, forward, it crawled. That motion may seem unimpressive now, in a world where wings beat, fins propel and legs leap. But 555 million years ago, the act of crawling across sediment was a revolution, one written not in thunder, but in the faintest of trails, left behind by a creature called Icaria wariutia. For billions of years, life had mostly floated or clung. It had built itself into colonies, algae, fractals and fans. It had drifted passively with water or grown rooted in microbial mats. Even the Ediacaran organisms, despite their otherworldly shapes, had remained still, letting the currents deliver what they needed. But Icaria was different. Tiny, no larger than a grain of rice. This soft-body, worm-like creature did something profound. It moved under its own power, and it did so with a plan. Its body was bilaterally symmetrical, meaning it had a front and back, a left and right, and the internal layout to coordinate motion accordingly. This wasn't a floating sphere or a featureless disc. It had direction. It had coordination. And most importantly, it had intention. Its name, Icaria wariutia, comes from the Ikara Flinders Ranges in Australia, where its trails were found in rock. These aren't dramatic fossils. They are gentle furrows. Tiny, sinuous lines pressed into ancient sediment, sometimes curving, sometimes branching, always with the quiet signature of a living body moving just beneath the surface. For a long time, these tracks were all that remained. But in 2020, scientists found the actual organism responsible, a faint oval impression only a millimetre or two across, preserved just above its own trail. It was the biological equivalent of catching footprints and foot together, the walker and the walk, united in stone. What makes Icaria so significant is not its appearance, but its place in the story. It is, as far as we know, the earliest animal with bilateral symmetry and directed movement, traits that would become foundational to almost every major group of animals that followed: worms, insects, mollusks, vertebrates, including, eventually, us. And it did all of this without bones, without a brain, without limbs, just soft tissues, muscles, and a mindless urge to move, perhaps to search for food or better conditions, or simply because its internal wiring compelled it to explore. Whatever the reason, that first deliberate journey changed everything. Because motion changes everything. With movement comes interaction. An animal can now encounter others. It can escape, pursue, explore, disturb the sediment, create patterns in the environment. It can navigate gradients of light, temperature, chemistry. Motion turns life outward. it opens the world, and with bilateral symmetry comes organisation. Once you have a front and a back, you can evolve a head, sensory organs, coordination centres, later nerves. Later still thought. Of course, Icaria didn't think. But it pointed in the direction that thought would one day follow. Imagine it now, drifting across the ancient seafloor, under layers of microbial mat gently wriggling its way forward, not fast, not graceful, but persistent, leaving behind a quiet wake in the sediment, like a whisper in the mud. You might miss it entirely if you look too quickly, but if you slowed down, if you listened with ancient patience, you'd see that this is where the story turns, not all at once. There was no explosion of limbs yet, no dramatic arms race. But in that moment, in that motion, Earth gained something new. Animals that could explore, that could act on their surroundings, that could begin, slowly, to shape behaviour. That change would set the stage for the Cambrian explosion just a few million years later. A burst of complexity, diversity and interaction. But before all of that there was this. One tiny animal crawling in silence. It is comforting, perhaps, to know that great transformations begin this way. Not with fanfare, not with size, but with something small, persistent, and curious enough to move through the world, leaving a trail behind. Tonight, as you drift to sleep, you might imagine yourself lying in a warm, shallow sea, the light dim and dappled, the bottom soft with silt. Near your hand, something moves, just a small ripple in the mud. It doesn't know where it's going, but it knows it wants to go. And sometimes, that's all it takes to begin the future. Time equals 2.0 seconds. After 4 billion years of fire and freezing, of breathless waiting and soft unfolding, after continents collided and microbes dreamed themselves into animals, after oceans remembered how to stir and life pressed its soft imprint into stone, there is you, lying here now, breathing in a room shaped by ordinary light, the hum of stillness around you, the weight of the blanket across your skin, a little warm, a little tired, and still holding within every cell the quiet echo of Earth's story. It's not just metaphor. You're made of ancient things. Your blood still carries the salt of long-vanished oceans, a quiet brine flowing through vessels that echo the rivers of ancient sea floors. Your cells, each wrapped in a delicate membrane, still whisper the same chemical language as the earliest single-celled life. The energy that fuels your every movement still flows from mitochondria, descendants of free-living microbes who once made a deal in the dark, long before brains or bones or eyes. Even now your body carries traces of the blue-green algae that turned sunlight into breath, long before the sky was blue. When you inhale, the oxygen slipping into your lungs isn't just air. It is history, renewed each second by the same process that painted rust into Earth's stone, that cooled the skies, that turned poison into possibility. Your breath is not separate from the planet. It is the planet breathing through you, and though the body you carry is new, born of recent years, shaped by modern life, its instructions are ancient. Hidden in every strand of DNA is a script billions of years in the making. There are genes in you that first danced in jellyfish. There are rhythms in your nervous system that mirror the movement of flatworms and fish. You're not merely walking on Earth. You are what Earth became when it wanted to walk. This isn't poetry. This is biology, written with tenderness. The hydrogen in your water came from the Big Bang. The oxygen from stars that lived and died before the sun was born. The carbon in your skin passed through volcanoes and forests, and the quiet bodies of things that no longer exist. Your bones were once part of mountains. Your calcium once floated in shallow seas. Your thoughts, even now, are powered by ions moving across membranes first invented by bacteria. When you lie down at night, When the lights go off and your breath slows, your body doesn't shut down. It returns. It drifts into the same ancient rhythms that once rocked trilobites in Cambrian tides. Your heartbeat is a tide. Your sleep is a season. You are, in every sense that matters, a continuation of everything this planet has ever been. And when you sleep, truly sleep, you are not leaving anything behind. You are returning. The world does not ask you to understand all of it. It doesn't need you to memorize every name or date. It only asks that you remember, somewhere deep and quiet, that you belong here. That you are not a visitor to this timeline or an interruption to its peace. You are part of the same story, a sentence following a long paragraph, a ripple following a wave. You are the memory of oceans, carried forward not in words but in warmth. So let yourself soften. Let your muscles melt back into the shape of the bed. Let your breath slow to the rhythm of Earth's deep cycles. In, like the tide coming home, and out, like the tide returning to rest. There is no urgency now. No need to carry the questions of today into the dreams of tonight. You have done enough. Let time go. Let it unfold around you like a blanket, wide, heavy, and without edges. You do not need to follow it. It will carry you gently, just as it carried the first algae, the first swimmers, the first spark of crawling life across the seafloor. The same hands that shaped them are shaping you still, in rest as much as in waking. The planet is not just beneath you. It is within you. Its history sings through your bones. Its chemistry pulses through your thoughts. Its softness, when you allow it, can cradle you all the way down into sleep. So go, gently. Close your eyes, if you haven't already. Let the weight of this long journey settle like dust, like snow, like sediment at the bottom of an ancient sea. There is nowhere else to be. You have arrived. You're a story told in starlight and stone, and tonight that story is allowed to rest. He is